Right. Yeah. So I am Nathan Egge, and I'll be talking today about this topic: AV1, Nits, Nitpicks, and Shortcomings, or otherwise titled "Things We Should Fix for AV2." Right. So very positive here. I've got a link to my slides if you want to download them and follow along. All the slides I make are always online. So who am I? As I said, Nathan Egge. I work for Mozilla. I'm head of our codec engineering team. That means I work on all things AV1 related. So I work on our Rust AV1 encoder, Ravi. Contributor to the David project. I go around wrangling people and trying to and get new contributors to these projects, try to get them engaged. I'm also a co-author of the AV1 format, and I worked on the Dollar project before that. And then recently this summer with Vimeo, I organized and co-hosted this Big Apple video conference. And so many of our speakers are actually in the audience here, so thank you. The talks were great. I encourage you to check them out. I'm also part of a number of nonprofits like Zip.org and the Video Land Association. And I generally advocate for royalty-free media standards and formats. So I'm wearing this really great AV1 shirt. I've actually manufactured and given away like 300 of these. So if you'd like this shirt, please contact me. I can get you one. So I wrote this abstract because I've been kind of participating in this AV1 community, and there's been a lot of interesting feedback about what was the work product that came out of AV1. And so I circulated this abstract, and I generally got this feedback from people who reviewed it that it sounds kind of negative, and like maybe we should focus on some of the positive things. And so what I want to do, I'm not even going to read the abstract. I want to start by talking about the accomplishments that AV1 made. And so it's pretty incredible if you look at the timeline of work that was completed. From the formation of the Alliance for AOMedia through to publishing the standard was really only about 30 months. Which if you've worked in this field, is kind of ridiculous that we can get that much work done. Now, of course, the only reason that was possible is that we started from a really strong point with 3 different code bases where we could draw from tools and techniques to make the standard. And so if you look at that same timeline, this is a graph that I like to show people because I think it's really impressive to see the gains that were made. And thank you to Steiner from Cisco, who's been maintaining this graph for me every time I go to give a talk. He helps by updating it. And so what you're looking at is AV1, libaom compared to itself, starting from the earliest point we have, which is back in July of 2016. And so what I haven't done before, this is the first time, is I've now overlaid those like inflection points from the previous timeline. So it's really interesting to see just how quickly progress was made during this standardization effort. And I think the reason for that is that we were able to do this collaborative effort between all the people in AOMedia. However, with a short timeline, there were also some challenges, right? And so integrating, coding tools, like the success was your coding tool integrated, right? And it was primarily based on metrics, and less important were things like the quality inflation or how well it integrated other tools or peer review. Mostly because we were just moving really, really quickly. There was not a strong incentive to fix implementation. So once it landed, you were really looking at the next coding tool because you're trying to get gains, and you weren't going back and rethinking it or refactoring it. And a lot of times, because of the process, we were required to keep these like work in progress patches. So I did the $EC patch. I actually maintained all 3 entropy coders for like maybe 12 or 16 months because we still need to be able to turn them back to the other one before that experiment had been enabled and approved. And so it's actually quite a bunch of work to do the process we had, and that's fine. I mean, it was a good process. But sort of towards the end of the cycle, lots of tools were enabled at once. And so the result is that many issues are now being found by implementers who are going back and looking at the standard. And I thought it'd be fun to take a look at some of the things that have come up during this implementation period and see what they mean for the standard, right? And of course, I already showed you the graph. The gains are good. Like the standard is a good standard. It's a good format, but there are some things that are kind of interesting. So as an example, this is something that Monty and Montgomery found. So in the self-guided restoration filter, there's this prediction logic, and several modes that make use of just the second coefficient. But if you look at it and work the math out, that V value is just always equal to 95, which was kind of interesting, and only showed up just through analysis. And so we actually told people about this And here it is added to the David decoder, just like remove all that logic and just there it is 95. So thank you to Luc Trudeau for doing that. So I thought that's kind of interesting and emblematic of or representative of the sort of things that we're seeing where it doesn't really impact the coding performance. It's just reading through the standard, you're like, huh, what is that doing? So here's another one that was really surprising and also in a good way. The deblocking filter that's used in AV1 is actually this mature continuation of the deblocking filter from VP9. It's been used for more than a decade. And when Monty was doing some analysis of it, he showed that you could actually separate the horizontal and vertical components and do optimization on them each individually. And what that meant was he designed a separable solution for optimizing it where it was an approximation of an exhaustive search, but he actually was very close to what the brute force did. And so this was an example where you could create an algorithm and there were no normative changes. It just was something that we hadn't expected to find. I've got two links there if you're really curious. One of them is Ravi compared to Ravi with this new algorithm, and it's getting gains like this because this was designed about a year ago, and Ravi was still missing some coding tools. But if you do the second link, it's a comparison of a brute force search versus this algorithm that shows kind of a negligible gain. So we were really pleased to see that, and not a bad thing to come across. And then the third example from the work that Monty was doing was looking at just the padding, cropping, and edge extension conventions for all of our filters. You can kind of pick whatever convention you want, but you want to stick with it. And we had these 3 loop filters, and they all kind of picked a convention and stuck with it, but they were different conventions. So no, not necessarily wrong, but it's a little confusing. So deblocking is clipping in one way and padding in a different way, and where the filter works, and it's different from what CDEF does, and it's different from what the self-guide filter does. Not necessarily wrong, but if you were an implementer and you were reading this, you might be confused as to why they're doing different things. The gains, again, are still good. And this is a picture of what that looks like. So they're all kind of different regions and have different behaviors. And so that may be something, when you're doing a pipeline implementation, having them all kind of match might make it easier. So another example, which may be more interesting, is this Quantizer Selection example. And so here the idea is, for a given frame, you can signal DC and AC quantizer indices for the luma and the 2 chroma, so up to 6. You signal 1, you signal a bunch of deltas, and you have 6 of them. And those indices map to a nonlinear quantization table. And so this is a graph of the quantizer index, and so it's a logarithmic graph. So the first half of 495 is actually linear. It's just curved because it's logarithmic, and then after that it becomes exponential. And so, if we take a simple example like flat quantization, that would correspond to just drawing like a horizontal line across this graph, and you could obviously pick the same quantizer for chroma and luma by signaling those quantizer indices. But what happens if you then want to boost that block, right? And so the idea is there, in Ravi we're doing temporal RDO, we're doing activity masking, we have the need to kind of increase the quality of certain regions of the frame, and the mechanism for boosting a block is you can signal a segmentation ID, and the segmentation ID has like a delta index. But that index is added to all of the quantizer indices, right? It's an offset of those. And what happens is, on the left side of that graph where everything's linear, you're going to scale the quality up uniformly. But once you get to the nonlinear side, you might give more quality or bits towards chroma than luma. And so, that might be a problem if you've gone through and done some work like one of our contributors did, where he created a lookup table to do a nice chroma-luma balancing. So you start with a chroma-luma balancing for your frame, and now you want to adjust it. Well, what do? Now you're going to get it off balance. And so there's this is not something we can fix normally, right? Like we've already made the bit stream. So there are two ways we could fix this. One is like an engineering solution, maybe for AV2. Where instead of coding a single delta index for that segmentation or that segment, you could just do the same thing that we did for the frame. You could code, a delta for, say, luma, and then you could code offsets from that, and you could use these bit flags to indicate whether or not those exist. So it'd be very, very cheap, right? To get the same behavior would cost just a few bits per segment, but then you could also have this new behavior where you could signal other quantization indices. The other solution is we could just do more science, right? We could go figure out what these curves should actually look like that give us that good chroma-luma balance. We could save on the coding cost, but it takes some time to do that work. And the point is, we didn't really look at this during AV1, but we should probably look at it during AV2 development. Another thing that was an experiment that we considered for the AV1 development process that ultimately didn't make it was this experiment called simple crop. So if you're familiar with how the cropping works in a AV1 frame, when you have a frame that's not multiples of a super block size, what you'll end up doing is end up coding this MI grid that is sort of rounded to the nearest 8x8 block. And so you get this kind of jagged edge along the bottom where you've got to code MI block, like the MI grid information. And there's a bunch of logic around how that works and how that interacts with other tools. And so, one idea that we had in Dala where we had a similar problem is rather than try to figure out which pieces we can code and which parts we can exclude, to just code everything, right? Extend it for the whole frame, code everything, but just make it really, really cheap to code the parts that are outside the visible frame. And you can do that by two ways. One is that you can adjust the predictor for that region so that it ends up being exactly what you're coding. So for example, you have a motion field and you can use just that predictor in the padded region. And the other is you can just bias it by adjusting your RDO. So when you do rate distortion optimization, you don't consider the distortion. You let that be whatever value it wants, and you only care about the rate. And so I've got a picture here of what this looked like in Dala. And so the gray part is the frame, and the red extended area in Dala was just the motion field. And so we would simply copy for that padded region exactly what the predictor was. And so this is as far as we got when we were doing this work in AV1. We'd identified the steps to get this experiment to work. We had figured out how to pad the MI blocks to the nearest super block. And then the next thing was to go through and fix all of the other experiments that had dependencies on this behavior. In doing that, enabling this thing, it would end up breaking all those experiments. We had to go through and fix those. And then we had the third step, which was making the padded region actually cheap to code. And so the first one was relatively easy. But going through and fixing all the experiments ended up being really hard. And when we did do that, we still were unable to make the padded region cheap to code. But in talking to both Tim and Tristan, who worked on this, they actually thought that this was a really good idea to bring back for AV2 because it meant that you could exclude a whole lot of logic that was sort of special casing that border. And also it ends up removing a bunch of special case stuff that only ever shows up when you're trying to adjust probability tables to code those symbols. And then the last example, I think, is probably one of the more promising ones. So we added this multi-symbol entropy coder. And the idea here was that instead of coding Boolean symbols, we would code these multi-symbols. We had an alphabet size up to 16. But in order to take advantage of that, you had to rework your alphabet to use symbols or to code symbols with alphabets up to 16. And so we added this LVMAP experiment, which changed the coefficient coder, which ends up being the bulk of your bits. And that used mostly binary symbols. And we added that kind of in February of 2017. And then later in the year, someone from ARM added this LVMAP multi experiment, which uses 4 CDFs. And so we were able to, use more of that multi-symbol arithmetic coder. And what's really interesting about this is if you look at this graph here, these are like 3 of the test clips we've been using with David, and I've got a histogram, like a normalized histogram of the size of the CDFs for those symbols, and the bulk of them are these 4 CDFs. And in fact, if you look at the commit message for this LVMAP multi, it reduced for a certain clip the number of adapted symbols from 6.7 million to 4.3 million. And so the idea is if we could use even larger CDFs, we could increase the number of the amount of information per symbol, the amount of bits per symbol, basically, and that would allow us to do higher rates because when you're doing a hardware implementation, you're serialized on the entropy coder, right? And so if it's running in hardware at a certain rate, you're not going to be able to decode any faster than that rate. This also has an impact on software decoders as well. All right, so what were the process improvements that were identified here? So one of the things that was really challenging was that there was not really an agreed upon end date, or at least it wasn't totally obvious during the development cycle. And so if we knew when this would be done, it would be easier to go back and say, while doing the development, we should prioritize, say, simple crop, because that one actually was within striking distance of getting completed, and we didn't prioritize that because we weren't exactly aware of when the endpoint was. Another good question is, what's a reasonable time frame between formats? I'm not sure I know the answer to that, but that sort of drives knowing that the answer to the first question. Certainly having a longer engineering review period would help. So a lot of the things I showed are showing up during implementation, but it would be great to find some of them during a time where we could still change the spec. And so one way to do that is to try to have a second implementation. And this was something that we did with Opus. So right before we published the Opus spec at the IETF, like Tim Terryberry went and implemented a separate decoder called Opus file that exercised a whole bunch of options in a very different way, and like ended up teasing out a couple issues. Obviously, there's been errata to that spec, so like nothing's perfect, but it got us closer to the way there. And then maybe just looking at encoders that have a lot of different operating points could be helpful. Although I think we did a really good job of hitting all the use cases. And then I think there's room to maybe get peer review from domain experts that were not as close to the implementation. So a lot of times the review was from people who were deep into the standardization process, and maybe getting some outside review from other experts would be helpful. And then maybe to balance some of the hardware and software implementation concerns, right? So I think we did an okay job. We might have been able to do a little bit better. All right, and with that, I will take any questions if you have them. One thing I'll add is I am trying to collect more of these. So I think that there's a lot of learnings in implementing new formats. And so if you have something that you'd like me to add to the list, I'm very happy to include that and keep track of that and maybe help figure out when they can be worked on.
Yeah,
Yes.
I just have a simple comment. So some of these ones, like the simple crop or any of the other ones, feel free to just push it up as a patch in the experimental branch.
Yeah, no, I like I said, I talked to Tristan, who actually was quite excited about being able to revisit that. I think the challenge is, there's a lot of things to touch, right? That was why it didn't make it the first time. It's just a lot of experiments, a lot of assumptions.
But the code is now much cleaner than what it was in 2017 or 18, so it should be much easier.
Yeah, no, I think one open question is, what impact does that have on existing hardware, right? So
yeah, I'm talking about the experimental branch, so that's not the master branch. So the master branch is for everyone. The experimental branch is for every2.
Okay.
Yeah.
You have the other microphone anyway? Somebody's taking it as swag, obviously. Oh, that's right.
Oh, sorry.
Oh, sorry.
One other thing I think might be useful is to maybe think about some kind of architectural design issues up front. One would be error resilience. So we evolved on that, and I think we arrived at a good solution in AV1, and I think works very well, of having resilience properties inherited through the primary reference frame. But that happened quite late in the day and involved quite a lot of refactoring right at the end. But if we could agree next time at the beginning whether it is that or something else, what the architecture for error resilience would be, and there may be other features where you think there needs to be an architectural design principle here. Scalability might be another one you might want to think about. So maybe have some kind of architecture themes, so that these things don't just kind of emerge from the tools that are thrown in, but we try to kind of abstract some of these properties that you want the codec to have.
Alexis, go ahead.
Just another comment. You mentioned quite a lot YCBCR and 4.2.0, but it would be nice to see more tests on 4.4.4, and not only on YCBCR, because YCBCR is just like a representation space. So CBCR are not really let's say physical quantities. Okay, so it might be nice to see what happens with RGB content. There are new color spaces that people are proposing, especially for HDR. Okay, I don't know how much HDR is actually being tested right now. Okay, but that's becoming more and more important. But just nice to see all those things being evaluated, not just conventional YCBCR, and look at beyond what we're doing right now.
Yeah, no, I think there's a couple of novel color spaces that have come up since then that I'm not sure anybody has evaluated it with. Oh.
Hi, I have a question about. Do you think it's beneficial for the codec to have a reference test suite with reference videos for AV2, and maybe are we still on time for releasing it for AV1 as well?
Yeah.
One of the things we're looking at for AV1 is to try and set up some reference streams. So we'll have a repository somewhere, and then maybe every one of the major streaming companies and anybody else who wants to take part can dump their representative streams into that repository, and we can make them available for public use. Well, they would be normative streams, so the streams, we'd make sure that they were compliant with the AV1 spec.
How much coordination are you having on those streams? Basically, it will be beneficial that each company contributes something specifically. How is done in other places that someone is focusing on maybe on the intra, someone is focusing on the deblocking, because otherwise we might be testing 10 times the same thing and missing others. I mean, we need to have a deep coordination.
Yeah, I mean, we could do that. I mean, the basic idea of that larger test set is to make sure for a given decoder, it can decode all the representative material from the big streaming services. What you're talking about is kind of an extension of that to make sure that we have optimal coverage of all the coding tools amongst that set.
Yeah, but what individual companies are using today will not be the case years from now.
Right.
That means we want to go wider than making sure decoders decode what we currently have.
You mentioned that in AV2, possibly software implementations should be given some more priority compared to the hardware. So do you have any particular suggestions, like what was not done right during the AV1 phase, or how would you address this concern?
I mean, I'm not sure I'm exactly the person to address it. I could certainly give you some ideas, but I mean, it should be something that we all agree to. But I know there was a hardware working group in the AV1 process. It might be good to have a software working group, right? That just looks at how well you can SIMD things, or will this work on modern laptops, right? Or how far back do we want the decode implementation to be deployable, right? I think we ended up at a really good solution, because we're seeing with David that AV1 can be deployed on a very broad variety of devices, but I'm not sure we knew that was possible when we were developing it.
I think the one thing to say there was that we do have this new subgroup structure. We have a software implementation group planned there, And the ideal thing there would be people would be optimizing the tools as we go for the software platform on the Intel and ARM platforms, so that first of all, it makes the development lifecycle easier so that we can maintain the complexity of the decoder and run tests a lot faster. But secondly, gives us immediate feedback on where the nits are in the software architecture.
That sounds great.
Would this software working group recommend hardware acceleration blocks?
Again, I think it's up to who shows up to do work in that working group, right? I know that in particular, we have people now looking at using GPU acceleration for parts of AV1, and I think certainly, some idea of things you could offload should be part of that. But I mean, again, it'd be up to the participants who show up to do that work.
I mean, isn't that part of the process that we'd want the evidence, and you'd bring that in and you'd show that it gave a benefit if we modified our structure accordingly to fit your hardware architecture, and then we could weight that input as to the sort of algorithms that we chose.
Some kind of common hardware architecture, I think it would be useful.
Do you have anything in mind? I mean, that would be great. Bring it in and we'll take a look at it.
Not yet.
Okay.
Another question related to the software implementations. So in AV2, should we consider multi-core implementations, for example? How well is the algorithms parallelizable, for example?
Yeah, I mean, I know that we did some amount of that for AV1, right? Like there were certainly algorithms that we designed knowing that you could use SIMD to do them efficiently. And I think, and I'm not going to speak for the whole group, right? But I think, the way we structured tiles and frame threading ended up being really efficient.
Okay, one last question. Two last questions.
Yeah.
I'll go on then.
Yeah.
Whatever.
I just want to say that, it's great that you put all this list together. And also there was a lot of people brought up very good points. I really think we should keep it a running doc or just keep tracking all these things we discovered, right? We don't want to end up when we go AV2 and we forgot about some of the things people already discovered in the process. So I don't know, maybe some of us should keep tracking all of the things. Seems like you have a good starting point already.
There are more. I mean, these were just kind of the interesting ones.
Yeah. So I actually just want to suggest that we should put something together to keep track of all of the things we discovered that we should fix, no matter when that fix is going to be. But I think we should keep track of them, make sure they are all fixed by the time we actually do next codec.
Yeah. And very quickly, just for clarifying, you mentioned that external reviewers are recommended. Would you recommend outside of AOM, within OM, people who are not involved in the actual algorithm development? Anything specific?
Yeah, I mean, so there are a lot of people who are implementing who aren't part of the AOM, right? And they've got valid implementation concerns. There are a lot of experts that, maybe are good at the implementation side and not the codec engineering side, and they're certainly qualified to tell you, I can do this in SIMD, I can't do this in SIMD, or I can do it in hardware and I can't, right? I think there's a lot of people who we could reach out to. And I don't think a review is a challenging thing to allow.
But you're talking AOM, right? Not really external.
I mean, we had people who looked over the work we did in DALL, and if they had good ideas, we had no problem listening to them. But I don't know, you can not take people's advice also, right?
Thanks, Nate.
All right, thank you.